Hello everybody, and welcome to the final video for Chapter 6. In this video we will cover Section 6.5, which is about the cheapest link algorithm. So let me just remind you where we are. All of Chapter 6 is about solving traveling salesman problems, which again are things like you're a delivery person, you have 20 delivery sites to go to before you return back to your home base. What's the cheapest way to go to those 20 places and return home? In Section 6.3 and 6.4, we saw three different algorithms for trying to solve these problems. In Section 6.3, we saw the brute force algorithm, which was optimal but not efficient, which means that it will give you the right answer. So you're looking for a cheapest route, it will give you a cheapest route. However, it takes forever to do for larger graphs, right? So for a graph with 4 vertices, it's okay, but for something like 20 vertices, 30 vertices, it can take millions of years to implement the brute force algorithm. So in 6.4, we turned our attention to a couple of different algorithms, the nearest neighbor and repetitive nearest neighbor, and those algorithms were not optimal, but they were efficient. So in other words, those two algorithms would give you a route, and they would give it to you quickly. So it's not that bad to implement. However, the route that it would give you, the delivery route it would spit out to you, might not be the best route. It might not even be close to the best route. Okay, it's giving you a route that you hope is good enough. So in Section 6.5, when we study one more algorithm, this algorithm is like the nearest neighbor algorithm in that it is not optimal, so it's not going to guarantee you get a best route, but it is efficient. Okay, it doesn't take that long to do. So Section 6.3 gave us the right answer, I suppose. But, in real life, if you are in charge of scheduling people's deliveries, you cannot wait on a computer to implement the brute force algorithm. Okay, as we saw in that section, you can wait millions of years for the computer to give you your answer. But you need an answer this morning. You need an answer in like 30 seconds. So Sections 6.4 and 6.5 are a couple of different algorithms that programmers actually will use to try to give them a delivery route. And again, these algorithms they're not guaranteed to give you the cheapest route, but they will give you a good route quickly, or what you hope is a good route. So here's the idea behind the cheapest link algorithm. The idea is to piece together a tour, sort of link by link or edge by edge, on the basis of cost. It doesn't matter if in the intermediate stages the links are all over the place, if they're not connected. If we're careful, at the end of the algorithm they will all come together and form a tour. So this is how it works. You look at the entire graph and choose the cheapest edge of the graph, wherever that edge may be. Once this is done, choose the next cheapest edge of the graph, whatever that may be, and so on. You can't just do this though, you have to follow some rules that we will explore later. But this slide without context I think makes very little sense. So let's explore this idea in an informal example. So here's an example we've looked at least once before. This is like you're going to drop a Mars rover on the surface and it needs to go to these separate sites and collect samples and then return back home. So maybe A is home base, it needs to go to N, I, W, P, H, G, back to A. And of course, it wants to do this while minimizing distance. So here's a graph that represents that situation. So notice the vertices here have the same labels as the vertices here. And all we've done is we've filled in distances from N to P, and from P to W, and W to I, etc. So I forget what the units were on these. They may have been miles, but this seems too long. So let's just say meters or something. So this means that to get from A to G takes 7,500 meters, and from G to H takes 3,000 meters, etc. So let's say that you are in charge of telling this rover where to go. And let's just say home base is G. I mean, who knows, right? But just for the sake of argument, home base is G. Okay, so you're in charge of finding a route that this rover will take, and you'd like for the route to be good, obviously. I mean, you would like to have a route that minimizes distance. Well, if you think about it, let's take a global view of this picture. What kinds of edges in this graph would we like to walk? Well, we wouldn't like to walk this one, would we? From G to N? That one's really high cost. In fact, it's the highest cost edge in the whole graph. We'd like to avoid things like that. We would like, though, things like this edge, this 1300 edge. That's the cheapest edge in the entire graph. So if possible, we would like for our route to go through this edge. So if we're at P, we would like to go to W via that edge, or if we find ourselves at W, we would like to go to P along that edge. Okay, so 1300, if I had a highlighter here, if PowerPoint would let me highlight, I would just highlight this edge and say, look, no matter what route we end up walking, we like this edge. We're going to go through this edge because it's the cheapest. Now, what's the next cheapest edge? So again, we sort of step back, we take a global view of this picture, and we see that 1500 is the next cheapest edge. So if possible, we'd like to go through that edge. Right? So we would have highlighted these two edges now. 1300 and 1500 are good for us in ways that like 8000 is bad. Right? And so now what's the next cheapest edge? Let's scan around. It looks like, what, 2000 is the next cheapest edge? So the next thing we would do is highlight that. So what we're doing is we are stitching together a path. So notice 2000 is not connected to this 1500 and 1300, right? It's up here. But what we're doing is we're saying, look, eventually we're going to stitch all these edges together. But for now, I'm just focusing on what edges do I like, you know? If I'm going to walk a circuit through this graph, there are what? 1, 2, 3, 4, 5, 6 vertices. Oops. I really should work on my counting. Including home base, there are 7 vertices, right? So I'm going to have to walk 7 edges in my circuit. If I'm going to start at G and end at G and visit every other site, I'm going to have to walk 7 edges. So what I'd like is for those 7 edges to be as cheap as possible. So I'd like for this PW edge to be one of those edges. I'd like this AP edge to be one of those edges also. And I'd like this NI edge to be one of those 7 edges. So far, 3 of the 7 edges in my path are accounted for. And they were the 3 cheapest in the graph. Okay, so contrast this with nearest neighbor. If I'm starting at G, right, nearest neighbor is just like, keep your head down and follow your nose along the cheapest path. So you do G to H, and then what would you do from there? You do H to W, right, etc. And then actually you would do P and then A. But nearest neighbor, right, it's very tunnel vision-y. You just, at the vertex you're sitting at, right, you only consider your next move. You don't ever step back and zoom out and look at the graph as a whole. It's just, okay, I'm at G, so I'm looking at 1, 2, 3, 4, 5. These 6 edges are what I'm looking at. I picked the cheapest down here. Okay, I'm at H. These 6 edges are what I'm looking at, but I can't go back to G. So these 5 are what I'm looking at. Okay, I go to W. So you're not ever just taking a step back and saying, well, look, globally speaking, which edges do I like? You know? So cheapest link is allowing it to do that. You step back and you say, look, I know I must travel 7 edges. Can I somehow control which 7 edges those are? Can I make them as cheap as possible? So ideally, the 7 edges you choose that you stitch into a path are the 7 cheapest, but not necessarily. So let's go back to our cheapest length thinking. We like this edge here, PW, highlight. We like this edge here, AP, highlight. We like this edge here, NI, we highlight. What's the next cheapest edge in the graph? So we step back, we look over the whole thing, and we notice AW is the next cheapest edge. So we'd like to highlight that too. We'd like to say, look, we have to travel 7 edges. I'd like AW to be one of those edges. But if you think about it for a while, you realize that that actually isn't possible if we're going to make a Hamilton circuit, if we're going to make a tour. Because I've already chosen PW, I've already chosen AP. So suppose I decide that AW is another edge I'm going to choose. Well, if I highlight this edge now, I've got a triangle here. I've got a closed triangle. If you think about it, that's bad, okay? Because if you have a closed triangle and you're going to travel around it, that means you're going to hit at least one of these vertices twice. So suppose I start at P. I have to go to A, and then to W, and then back to P, but I've already been to P. You know, I can't go back. Or maybe I'm at W, and I do the triangle this way. W to A to P, P back to W, but I'm not supposed to do that. Once I leave W, I can't come back. So when you're taking these steps back and like trying to highlight cheap edges, you have to be smart about it. You can't just choose the cheapest 7 edges. If you do that, there's no guarantee you're actually going to have a circuit that starts and ends where you want it to. But in any case, this is all informal. I haven't shown you really what to do yet, but this is the idea. You want to step back, look at the graph as a whole, and start choosing cheap edges. And if you do it intelligently, then hopefully by the end of it, you will have cobbled together a good enough path. It might not be the optimal path. There's no guarantee of that, but hopefully it will be good enough. So here's a more formal description. So don't worry if edges that you highlight aren't adjacent to other edges. So remember in this example here, I highlighted PW first. I highlighted AP next. These two guys were next to each other. But the next edge I focused on was this NI, which is not next to either of these two edges. But that's not a problem, okay? In the end, we're going to stitch together these edges to make a continuous path. So, as I've said before, we zoom out, we highlight edges, okay? And you highlight the cheapest thing available. But there are 2 rules you must follow. Do not allow a circuit to form except at the very end. Okay, so let's go back to the example. I highlighted PW, that was my first edge. I highlighted AP, that was my next edge. Then I highlighted NI. None of those highlights form a circuit. But as soon as I highlight AW, notice that I've closed a circuit off, right? So remember, a circuit is basically just a path that starts and ends at the same place. Well, a triangle is like that. WP, PA, A back to W, okay? So I'm not allowed to do that. I'm not allowed to form a circuit until the very end. When I highlight my last edge and now suddenly I have a circuit that starts and ends at G, or wherever it's supposed to start. Okay, the other rule is do not allow 3 edges to come together at a vertex. Okay, so what does that mean? That means that in a picture like this, if you're highlighting edges, you can never highlight 3 edges coming out of the same vertex. So suppose you've highlighted, okay, so in this example here, we've highlighted PW, we've highlighted AP. Well, notice there are 4 more edges coming out of P. But no matter how cheap they are or whatever, we can't highlight these 4. P is now done. The reason is that in a circuit, you hit each vertex exactly once, right? In a Hamilton circuit, you hit each vertex exactly once. So if these 2 edges here are highlighted, AP, PW, that means we come into P along one edge and we leave P along the other edge. And that's it. You can't go back to P, or maybe we come into P this way and leave P that way. But that's it. You can only visit a vertex once inside of a Hamilton circuit. So this little rover that's moving around, right? Once it visits P, it's not going back. Okay, so these are the 2 rules. As you're highlighting edges to cobble together a route, don't allow a circuit to form except at the very end. Also, never highlight 3 edges coming out of the same vertex. A violation of either of these 2 rules will prevent a Hamilton circuit from forming. And that's bad because you want a Hamilton circuit. You want to visit each vertex once and only once. On the other hand, if you follow these 2 rules, you will be guaranteed that once you're done, the end result will be a Hamilton circuit. So we're going to do an example, but just remember what the idea behind what we're doing. Let's say that G is home base, right? We are trying to plot a route for this rover that minimizes overall cost. Well, how would you do such a thing? Well, one strategy is to take a global view of this graph and say, well, look, the rover has to take 7 steps, doesn't he? Because there are there's 7 delivery sites and he has to come back home. So 1, 2, 3, 4, 5, 6, 7. Oops. Have I been misspeaking this whole time? 1, 2, 3, 4, 5, 6, 7. No, okay, good. Anyway, the rover has to take 7 steps, right? I would like to make sure those steps, individual steps, are as cheap as possible. So, given that he must take 7 steps, I'd like this to be one of those steps, right? This is the cheapest. I'd like this to be one of those steps too because it's the next cheapest. I'd like this to be one of those steps too because it's the next cheapest. And then I'd like this 2200 here to be the next step, but I can't make it the next step because if I highlight this edge, then I would be forcing the rover to make a little sub-circuit like this. And that's bad. You're going to force the rover to visit at least one site twice, and you shouldn't do that. But that's the idea of what's going on. You're going to cobble together, globally, cobble together a Hamilton circuit, and that will be the path that your rover walks. Okay, so here's an example that's smaller. This only has 5 vertices here. This is the original traveling salesman problem. Okay, so the salesman's up here at A. He has to travel to the other 4 cities and go home. So if you're doing nearest neighbor, you would of course go from A to C, right? And then what? C to B. C to E. And then what? E to D, D back to B, and B back to A, right? You do something like that. That's because you're just following your nose. Take the cheapest step, take the cheapest step. Now at cheapest link, the first thing we do is we say, well, what's the cheapest step inside this graph globally? Well, the cheapest step is this 119 link here. So we're going to highlight it. So notice that our cheapest link path will agree with our nearest neighbor path, at least for the first step. Okay, now we take a step back and we say, what's the next cheapest edge? Well, the next cheapest edge is this 120. So we're going to highlight that too. So again, this is following our cheapest link path here, or excuse me, our nearest neighbor path. That's okay. Now we take a step back and we say, well, what's the next cheapest edge? The next cheapest edge is this 120. Sorry, this 121 right here. We'd like to highlight that edge, but we can't, because if we did highlight it, we would have 3 highlighted edges coming out of C. That's not allowed, okay? Because we've already entered C and left C. So you can't highlight another edge going into C. So 121 is off the table. What's the next cheapest link? The next cheapest edge is this 133, okay? I'd like to highlight that, but remember, one of the rules is do not allow a circuit to form except at the very end. Well, if I highlight 133 now, I've formed a circuit. A to C, C to E, E back to A. So I can't highlight that yet. I'm not allowed to close the circuit yet. So 133 is also off the table. Okay, so what is the next cheapest edge? The next cheapest is 150. If I highlight 150, I haven't broken either of the 2 rules, so that's fine. So the next thing I'm going to do, I guess I should have, right, so as we discussed, right, you can't do BC, so we're not going to consider it anymore. We're not going to do EA, so we're not going to consider it anymore. And as we just said, the next cheapest link is 150, and 150 doesn't violate our rules, so we highlight it. Okay, what's the next cheapest edge? The next cheapest edge is this 152 edge. So can we highlight that? Well, if we highlight it, we're not breaking, let's see, which rule is it? We're not breaking the second rule. It says do not allow 3 edges to come together at a vertex. So can't have 3 highlighted edges coming out of a vertex. Okay, so if we highlight 152, we haven't broken that rule. What about the other rule? If we highlight that, will we form a circuit prematurely? Let's see. D to A to C, C to E. No, we will not have prematurely completed a cycle. So we're going to highlight 152. Okay, now what's the next cheapest link? The next cheapest link is what? 174. But we can't highlight that because there are already 2 highlighted edges coming out of D. Oh, this just finishes it for you. Okay. What about 185? Can't highlight that because there are already 2 edges coming out of A. What about 199? Can't highlight that because that prematurely closes a circuit, and also because there are already 2 highlighted edges coming out of D. So what's left is this 5th link here. The heaviest edge in the graph is 200. So here is the overall path we will walk. A to C, C to E, E to B, B to D, and back to A. That is the cheapest link tour. The total cost of this tour is $741, which, if you remember our previous example where we did this nearest neighbor, is a little bit better than nearest neighbor. But it's not as good as repetitive nearest neighbor. Repetitive nearest neighbor gave us $722 or something, if I remember correctly. So anyway, it gave us a good tour, but certainly not the best tour. So cheapest link is more confusing than repetitive neighbor, or nearest neighbor, sorry, than nearest neighbor. But the global idea, I think, is pretty intuitive. The global idea is, look, here's my original graph, right? I have to somehow walk through this, starting at A, visiting each other's city, and returning to A. Well, I'd love to walk this 119 edge if I have to walk, right? I'd love to walk this 120 edge too, right? I'd also love to walk this 133 edge, but given that I'm walking AC and CE, I can't walk this edge either. It will make me return to A too early. So the next edge I should walk is this 150, I guess is what we ended up with, right? 121 is off the table. So 150 is not connected to 119 or 120, but that's okay because we're just globally cobbling together a path here. And in the end, notice that it all came together, right? In the end, when we highlighted our fifth link, we ended up with a circuit. So that was okay. Okay. So here again is a formal description. Pick the cheapest edge possible. And of course it's possible also there might be more than one cheapest edge. You can pick any of them that you like. It doesn't matter. Mark it. So highlight it like in red. Pick the next cheapest link available on market. And then keep going at the very last step. And you have to keep going according to the rules we discussed, right? You can't prematurely close a circuit to create a circuit. You also cannot have three highlighted edges coming out of the same vertex. At the very last step, connect the last two vertices to close the red circuit, and that will give you the cheapest link tour. Okay, so again, there's no reason to think that this will give you the best tour, the optimal tour, but it will hopefully give you a good tour, and it's not that hard to implement. It takes way less time than the brute force algorithm. So let's solve this original traveling salesman problem from the beginning of the video using cheapest link. So I guess the home base is A. So he's sitting at home base. The rover has to go to all the other 6 sites, 6 sites, and return back to A. And of course the rover wants to visit each site exactly once. The distance is, oh, it is in miles. Man, that's a long ways. 8,000 miles? Okay. So anyway, they're given in this graph, which we've already looked at a little bit. So let's look at some of the approaches we might use to tackle this problem. Brute force would require us to check 6 factorial, which is 720 different tours. That's not a big deal for a computer, okay, but it is a big deal for you. You would have to make a table with 720 rows in it, I guess. So we're not going to do that. We can also use nearest neighbor or repetitive nearest neighbor, but for the sake of this video, let's use cheapest link. It will not take us nearly as long as it would take us to check all of these different tours. So a summary of what happens is in this step here, and notice that these first 3 edges are what I said we should highlight to begin with. So let's go back to the picture. PW is the cheapest edge in the graph, highlight it. AP is the next cheapest. Doesn't violate a rule to highlight it, so highlight it. NI is the next cheapest, doesn't violate any rules to highlight it, so we highlight it. 2200 is the next cheapest, but it violates a rule. It closes a circuit, and we aren't allowed to close a circuit till the end, so we don't highlight that. So that's why it says right here, AW, if we complete it, then we complete a triangle. So we can't do that. Okay, so the next edges, let's look. What are the next cheapest? So 2200 was out. So the next cheapest edges are HW. I can highlight that. That's fine. That doesn't close the circuit. So now we got these 3 edges here highlighted. And we have this edge highlighted. And AI also has weight 2800. If I highlight that, I'm also not breaking any rules. I'm not closing a circuit, and I'm not causing 3 highlighted edges to come out of the same vertex. So what I have so far is this is highlighted, as is this, as is this, as is this, as is this. Okay. And then finally, you can check this yourself, right? IW is the next cheapest at 2900. You can't close it or you can't highlight it because you'll cause 3 edges to come out of the same vertex. IP is in the next cheapest, and you can't highlight it because it closes a circuit. It also causes 3 edges to come out of the same vertex. GH is okay. 3,000. Once you highlight GH, you can again verify this on your own. The only way to close the circuit is GN, which has weight 8,000. So a pretty hefty cost here at the end. So here's what the root ends up looking like. This GN edge is humongous, right? We would have liked to avoid that, but the cheapest link tour is what it is. APW, HG, NIA. So here's what it looks like inside the graph. So basically, imagine this 8,000 weren't highlighted, right? Imagine that we're gone. You've got the other 6 edges highlighted, right? You have to get back to G, so the only way to get back to G is to highlight this edge. And then you've closed the total circuit, and the rover will have to travel more than 21,000 miles. Just for the sake of fun here, let's do nearest neighbor on the same graph and see what happens. So let's do nearest neighbor. So where's the original graph? Okay, so starting at A, where should we go? Go down to P, P to W. From W, where do we go? Looks like we go to H. From H, where do we go? We only have 3 options. 3,000 is the cheapest, so we go to G. From G, where do we go? Well, either 6 or 8,000, so we go up to I to N, and back to A. So the nearest neighbor algorithm just takes you around the outside of this heptagon, septagon, I don't know, the 7-sided figure. Okay. So if we do that, you can verify this yourself. You'll get a total path of 20,100 miles. So compare and contrast that with 21,400. The nearest neighbor saved us, what, 1,000 miles, basically 1,300 miles. That's pretty good. And here's what it looks like. Yeah, it just goes around the outside here. So if you are actually in charge of plotting the route for this rover, like I said before, 720 possible circuits, a computer can handle that. So you would actually just have a computer do brute force. But if you didn't want the computer to do brute force, you would essentially have it do both cheapest link and nearest neighbor, or repetitive nearest neighbor, and have it choose the best of those. In this case, nearest neighbor does pretty good for you. So actually, in this case, the nearest neighbor gave us a better tour than cheapest link, right? It did better by 1,300 miles. Sometimes cheapest link does better than nearest neighbor. So there's really no way to tell ahead of time which is going to do better for you. So in practice, people would just do both and pick the better one. The 2 algorithms are different but of equal standing. Neither one can be said to be superior to the other in terms of quality of tours it produces. Okay, they're both, in general, they're both pretty fast, and they both will give you reasonably good tours. They will rarely give you the best tour, but they will give you good tours. In this case, actually, the nearest neighbor algorithm gave us the best tour. And you can verify that using a computer, which of course you won't do. But let me just tell you, in this rover example, the nearest neighbor tour turns out to be the best. So the simplest of all methods happen to produce the best answer, which rarely happens actually, but it's nice that it happened in this example. So in this case, since nearest neighbor was the best, we can actually definitively say how bad cheapest link was in this example. It just was 1,300 miles off, which is pretty sizable, I suppose. Okay. So anyway, that's the end of Chapter 6. With Chapter 5 and Chapter 6 combined, you can now actually solve all sorts of real-world problems that have to do with just getting around, right? Navigating through the world. Navigating through the world costs. It costs time, or it costs distance, or it costs money, it costs whatever, you know. And these tools that we've learned in this chapter are implemented all the time by computer scientists, by programmers, to solve things like optimal delivery routes, or optimal parade routing, optimal patrolling, things like this. So if you students were computer programmers, you know, if you had some sort of programming experience, we would do all that. You know, we would just try to figure out an optimal path for a UPS delivery man. But of course, programming is not a prerequisite for this course, right? So we're not going to do that. But hopefully, Chapters 5 and 6, this introduction to graph theory, has been a nice sort of digression for you. This is not standard material you would see in a standard math course, but it's used all the time. It's used all the time in the real world to deal with just navigating through the world. So we are now done with Chapter 6.